Okay, so this is problem 55 of chapter 6 of Giancoli 6th edition. So what we have is a wood block, and the mass of this wood block is given to us, and it is attached to a horizontal spring, and they also give us the spring stiffness constant. Okay? And the idea is the following. Here we have our spring, and we have this block, this box attached to it. What we are going to do first is we are going to compress the system, the block and spring, and we are going to compress it by 5 centimeters. Okay? So this X here is 0.05 meters. Okay? And after that, we release the system. We release the system, and what we'll see is that the box will move, the spring will stretch, will pass through its original, its natural length, but it will keep on stretching a little more until it reaches this new position when it finally stops. Okay? Now, so it stretches by this amount, which is a little bit less than what it was compressed. This is 0.023 meters, so 2.3 centimeters. Okay? So how can it stretch a little bit less than what it compressed? Well, there is some losses involved. So mechanical energy is not conserved in this problem. And the question of the problem is exactly that. What is the coefficient of kinetic friction? So the question of the problem is what is the coefficient of kinetic friction? Very well. So how are we going to solve this problem? I'm going to start with this point. This I'll call point 1, and this final scenario, point 2. Okay? And I'm going to use conservation of energy. Conservation of energy, but not conservation of mechanical energy. So the idea is the following. We know that the net work is the sum of the work done by conservative forces and work done by non-conservative forces. We learned from the work energy principle that the net work is given by the change in kinetic energy, and the work done by the conservative forces is minus the change in potential energy. Okay. Non-conservative forces involves, for example, friction. In this problem, that's what it is. That's what we are after. And we know that the work done by a friction force is against the displacement, so we know we should put a negative sign, friction force, and the displacement. Okay, let's play a little bit with this equation that we just wrote, and let's rewrite it in a more familiar form. So the change in kinetic energy is the final minus the initial. The change in potential energy is the final minus the initial. And we have here the work done by this non-conservative force, which is the friction force. Okay? If we rearrange this equation, we find that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy plus the friction force multiplied by the displacement. So this is something that we already saw in class. It's just a quick revision. So the initial is what happens in point 1, and the final is point 2. Okay, so we start the motion by compressing this spring. So once we compress this 5 centimeters, we have no speed. So the initial kinetic energy is just 0, but we have a lot of elastic potential energy given by 1/2 of k x squared. X is 0.05 in our case. Okay, on the right side, what we have? Well, the box, this block moves until it stops. It stops when it reaches its maximum stretching capabilities. So it stops, final kinetic energy 0. So we have just the potential, the elastic potential, energy 1/2 of K, and the stretching here is 0.023 squared. Okay? Now, the friction force. What we are actually after is the coefficient of the kinetic, the coefficient of kinetic friction, right? So instead of writing the friction force, I'm going to write it as plus the coefficient that we are after. Now comes Fn, but remember, so what I'm using here, the friction force is mu Fn. In this problem, we are in a horizontal surface. There is no additional forces in the y direction. I know that Fn is just mg. Okay? So I have here mu mg, which is the normal force, and the displacement. Okay? So everything I have, the k here was given to us. And d also I have. The mass was given to us, and the d also I have. D is the whole displacement from the point where we had compressed all the way to the stretching. So this d here is that 5 centimeters plus 2.3 is the total displacement, so it's 0.073 meters. And so we get our unknown, our coefficient of the kinetic friction.